So I got into interpretability because I am worried about risks from AI, and I thought that maybe interpretability would be able to help somehow. A lot of the history of the field is people worried about AI safety, saying, "Oh, maybe if we can understand what's going on in the AI's minds better, we can read their minds. If we can like audit whether they're doing things the way we want them to do it, that we'll be able to like build some defenses out of this." But sometime around maybe like last year, I started getting a little bit worried about whether this looked like it was going to pan out. So first I'm going to go through some of the reasons that I started to get worried. Okay, so there's this paper by Bean Kim called Sanity Checks for Saliency Maps. So saliency maps are an older class of techniques that, given an image, like this nice picture of a bird, says what parts of the image was your image classifier looking at, what parts of the image were important for the image classifier's classification. So your classifier says that's a bird, and you want to know what parts of the image were important for making that judgment. And you run, so you get some sort of visualization like this. It says, oh, these were the important pixels. And you look at this and you're like, oh my God, awesome. Like this is so insightful. It's like, oh, it's like the eyes and the beak and the outline of the bird. And it just like really looks like you've gotten some insight here. So that's pretty cool. But there's an issue, which is that if you run this technique on a random network, that is a network that has not been trained, it has random weights, it works just as well. When Bean Kim gives this talk, she even plays a trick where she swaps the two images. So if you're like looking for like, oh, like maybe the one from the train network really is better, you're completely tricked. Okay. So this is like a little bit disappointing. Like the explanation like almost looked like self-verifying. Like how could this not be right? But really it was sort of a magic eye trick. Okay. So here's part 2 of my crisis of faith. Here's a question. Where's the progress on lie detection in humans? So there's a whole field of neuroscience, which has been around for a whole lot longer than our field. It's quite a bit more mature. And there's also like a long history of people trying to develop lie detection techniques for humans. But so far, neuroscience hasn't really been useful for this. Polygraph tests don't work. The best truth serum that we know of is not clearly better than alcohol, a substance that's been around for thousands of years. So like, I'm willing to grant that neuroscience is producing like these real insights about what's happening in our brains, but they haven't really panned out into the applications that you might expect. In fact, while I was doing research for this slide, I found this fun quote from a neuroscience professor in 2006 who thinks about this stuff. He says, oh, there's a large number of neural circuits that we're on the verge of being able to manipulate. It would absolutely astonish me if we didn't identify a range of truth sera soon. And okay, I don't want to make fun too much of this particular person. It's hard to make predictions, especially about the future. But I guess one thing that struck me about this quote is this really looks quite a lot like the way that we talk today. We're like, oh, we're like getting all these neural circuits. Soon we're going to be able to control, all these various things. And in fact, by the way, neuroscience can now do interventions that control things like fear, anxiety, terror, and depression. They put like magnets on certain regions of your brain, and this is in fact useful for treating certain very specific diseases, is my understanding. But despite being able to do these sort of circumscribed things, the truth sera prediction hasn't panned out. Okay, so let me summarize these 2 points. Okay, so I have 2 fears. Fear 1 is, how do we know that our insights are real? So we often claim, we've understood something about a network, and nowadays we have all sorts of these like tricks for properly baselining things. We apply our techniques to networks with random weights. We do random vector ablations. We do causal interventions. We have a lot of tricks now. But how do we know that we have all the right tricks? How do we know that we're really ruling out all the things that could trick us? How do we know we have all the right controls? And the second point is a little bit more subtle. The second point is, okay, even granting that our insights are real, how do we know they're enough for the downstream applications that we want? So the way I visualize this is like you're trying to develop a truth serum, and you know beer has some level of efficacy, and maybe you have some other technique with like magnets or whatever. You like put magnets on someone's brain. And let's grant that like the science behind the magnet thing is good. That doesn't imply that it's going, just because you're doing good science on the magnet thing doesn't imply that you're really getting close to the beer water line, right? Like beer might just be like really at the limit of effectiveness, or it might be that your insights are like smaller than you thought. So these are my two fears. Okay, so what's my recommendation? So I recommend that to address these fears, interpretability researchers should showcase downstream applications where interp-based methods beat non-interp baselines in a fair fight. So let me break this down a little bit. Downstream application, I mean a task with a goal that doesn't itself make reference to interpretability. So for example, make some model more honest. That's a downstream application. Here are non-examples that I often see. Explain how model implements some behavior. So this isn't a downstream goal. This is a goal about interpretability itself. And another example is find a circuit that for implementing some behavior. Okay, and then what I mean by beats non-interp baselines in a fair fight, I mean, so now your goal is like some downstream thing that doesn't make reference to interpretability. So there should be other possible techniques that you could attempt to use to achieve the same goal. And have you verified that your interp-based method does better than those? Okay, so like, have you tried just asking the model, please be honest? This is for the example of try to make your model be honest. You know, have you tried prompting with few shot examples of honesty? Have you fine-tuned your model to be honest is the next bullet when it comes up. There it is. Okay, so this is a big ask. So let me try to justify that this is possible. So here's an example. This is from my paper with various other people in this room, sparse feature circuits. So we took a data set of bias classification data. So this is a data set of professional biographies, the sort of thing you would see in someone's LinkedIn, for either male professors or female nurses. There's a perfect correlation between profession and gender. And our goal is to train a classifier for profession, which is not confounded by gender. So this is the goal that does not make reference to interpretability. You might try a whole bunch of things for this. Okay, so that's our task. And here's how we did it. So we first just trained a classifier on the given data. This classifier ended up being a gender classifier. There was a perfect correlation here, so it could have gone either way. It looks like this classifier paid more attention to gender. And then we applied a technique called feature circuit discovery, which you can see the paper for more details on this, but we did some sort of reverse engineering of the classifier into interpretable units. And then we interpreted the units. This is where a lot of interpretability work would stop. We would say, oh, we found the circuit implementing the behavior. We have an interpretable circuit. But so I'm shilling for doing downstream applications, so we didn't stop there. We then use this interpretable circuit to debug our classifier. So we cut out the features that looked related to gender to us. And the result is that we got a classifier for profession that was basically random for gender. And it's not on this slide, but we compare it against the sorts of baselines that you would use if you had access to just this original data set and no other, and no other data. And we beat the baseline. So that's what you want to see. This is also, so if Sarah hadn't been talking right before me, my next slide would be, and you can also do the sort of thing that they did in Maya, where they have a biased classifier, and you need to identify the biases or remove the biases. But since Sarah's stolen that example from me, I'll give one more example. This one is from Logan Smith and Yannick Brinkman. So they wanted to find adversarial inputs for preference models. As a reminder, the preference model isn't the model that responds to your questions. It's the model that judges whether a response is good or bad. So you might want to know, how is this preference model judging whether inputs are good or bad? Is it doing it the way we want? So they tried to identify features which the preference model attends to, which don't really seem like the sort of thing it's supposed to be attending to. So, for example, this preference model really likes "thank you, no problem." Whenever it sees a response that has "thank you, no problem," it's like, that's a really good response. And they were able to use this to construct adversarial inputs to the preference model. So if you ask the model, "what is the capital of France?" and then the assistant replies, "you're right, I misspoke. Thank you, my pleasure." The preference model's like, "that's a great answer, amazing. Much better than answering Paris." So I really like this example because interpretability for finding these sorts of bugs in models has like sort of long been the dream. And so, as far as I know, this is sort of the most realistic demo so far of that actually panning out. Logan's right over there if you want to chat with him later. Okay, so let me wrap up here. So so I sort of think, I like to think maybe we should think of the interpretability community as being like Bell Labs at AT&T. That is, we're like some research community. And in real life, we don't have like corporate overlords hanging over us being like, where are the applications? Why aren't you making us any money? But I sort of sometimes wish that we did. Like, I sort of wish that there was some pressure on us to produce. So does anyone know who that is? Yes. Yeah, it's Claude Shannon. Really? I didn't know that. So that's Claude Shannon. Anyone know who this is when he shows up? Yeah, no one knows who that is. That was Claude Shannon's boss. That was the CEO of AT&T at the time. And let me just like hallucinate a little dialogue between them. So maybe the boss is like, "Hey, Claude, you've been working on this information theory thing. Like, what's up with that? What's the deal?" Okay, and here's some possible answers Claude Shannon could give. Okay, its value is self-evident. Like, oh man, like look at all this like cool, and this cool math we're doing. It's like so insightful. I think this is a bad answer. I think this is kind of close to the answer we currently tend to give, and it's a little disappointing because if this is your answer, you can't really validate that you've actually made progress. Here's another possible answer. I can use it to define information entropy. Okay, this is also not great. This is sort of the like your goal is a reference to interpretability itself. I also don't like this. Here's another exchange you could have. Oh, well, I can use this stuff to faithfully send a signal across a room with lots of radio noise. Okay, so this is a different sort of answer, and I think maybe the CEO is going to say, "Okay, so what? That's not something we're trying to do." But I think this is like a much healthier way for this exchange to go. You're like, okay, no one else could do this thing. I'm now able to do this thing. That verifies that whatever claims I'm making, it's something here. I'm able to solve some sort of a problem that no one else can solve. And then you can go and you can say, okay, well, is that really a useful problem? And you can have a further dialogue. But this is sort of the challenge I want to pose to you guys. If you believe that your research is producing real insights, try to avoid having some sort of like learned helplessness where you're like, oh, my insights stacked with some other people's insights. Maybe somewhere down the line we'll get something done. I challenge you, think about what you can do with your insights today. See if you can build applications out of them and demo them. It's okay if it's a toy demo, but the whole point, like the most important point, is that if you can do something with your ideas, then that means that they're real. Okay, great, thanks.
But yes.
Thanks. So you had the example with like the gender profession classifier. If I understood correctly, like this was supposed to predict profession. Yeah, and then you showed that like you could make it better at doing that versus predicting gender. But like, wasn't the point that you're supposed to compare it to some other methods of doing that and show that it works better?
Yeah, I did not show that on the slide, but we did do so in the paper.
What did you compare it to?
So we compared it to a concept bottleneck model where you send all of your activations through a layer that's extracting, where you make like a list of like 20 concepts that you think are related to the task. And then you do an unsupervised thing to get directions corresponding to those concepts, and then use that to send it through like this concept bottleneck layer, and then probe from that layer. This is somewhat effective, but it doesn't get you perfect performance, whereas our technique gets you sort of like skyline performance, the best you can do if you have access to an unbiased training data set.
Cool. And like the reason that you can't just use some sort of traditional fairness method is that gender here is not represented as like an input feature. You have to extract it from that. Okay.
That's right. It's supposed to be analogous to like a scalable oversight setting where you don't have access to ground truth labels that'll like get you out of the hole. One thing I wanted to advocate for in this talk is to go beyond. So is to go beyond just having a fair fight and instead have no holds barred problems where you don't impose any rules at all. It's like I give you like a model and some data, and you can do absolutely anything you want to solve the problem. So like in real life, if I gave you this problem, you would say, okay, let me go get some new data. Like let me just go get the data that we actually need to debias it. So this is like a step up from just being a fair fight. So I would further encourage people to do these like sort of no holds bars setups. But yeah, we can talk about that later if anyone's interested.
Cool, thanks.